thank you also for the introduction. It's been 10 years, I think, that I was here last time at KITP, so it's a pleasure to be back here and talk about the link between turbulence and star formation. So it all starts with turbulence and it all sort of ends with turbulence again. And then also it ends with the presentation. Anyway, I'll see if I can, this is the pointer. Okay, sorry about that. So it starts with turbulence and it sort of ends again with turbulence. What I mean with that is that we need the turbulence, or we know that the turbulence plays a key role in structuring the gas, in smashing the gas around and sloshing all the material we see in the interstellar medium. And so it generates these dense structures from time to time, and they are then dense enough to collapse to form stars. So turbulence is really an initiator, a very key process in star formation. Once we have stars, we have lots of feedback things like supernova explosions or ionization that drives motions. We also have on smaller scales, I think I'm just not presenting the right presentation, sorry about that. Those are the slides that should show up online, so this is the actual talk. So on smaller scales, we actually have also these jets then again from the stars that form at these pillars, for example. So all of these processes can drive turbulence again. So we close this feedback loop of driving turbulence. So star formation is very inefficient, which means we have lots of gas, but we form stars at a very low pace or very low rate. And we know gravity wants to pull gas together to make stars real quick, but then we have this process of turbulence that also helps promote star formation by putting gas together in certain places. But in most of the other places, it makes the gas more diffuse and it adds turbulent motions that will ultimately counteract gravity. So turbulence is also a process that makes star formation inefficient. Then we have magnetic fields. Of course, the magnetic pressure also makes star formation inefficient. Ultimately, we have feedback on small scales. So to study these processes, we often do these numerical simulations where we can control the different processes and put them in one by one. So for example, if we have gravity only, we get very, very fast, efficient star formation in these dense filaments. At the knots of these filaments, we form lots of these stars. If we have turbulence, we can actually keep this material moving around without coming together very quickly. So that reduces star formation rate by about a factor of 2 or 3 compared to gravity only. So this plays already a key role. Adding magnetic fields slows the process down by another factor of 2 or 3 or so. And ultimately then when we have jets on small scales, so that stuff that would normally fall onto the star from the accretion disk onto the star will then be flung out in these jets. So there's already a clear reduction in the star formation efficiency and rate, but also, of course, we re-inject material. You can see these jets, how they sort of inject material back into the interstellar medium. So taken all together, with these processes, we get a star formation rate that's nearly about right. There's also, of course, radiation effects that have not been included in these simulations. And this is just so a bit of a diversion from the turbulence now. If you're interested in how to model radiation, which is really complicated, we've had some success in developing a variable adding tensor method in our code that does a bit better compared to other approximations of radiation transport. For instance, you get shadows here by these two sources. And there's also an application on this for massive star formation in clusters, where when you increase the surface density here from the top, low surface density, the UV really pushes out the material from the star clusters here. But if you have very high column density, the UV can't really act to do that, and also the infrared doesn't get out. So there's not much of an effect if you have a super dense environment. The radiation doesn't do much there. So back to turbulence. We know that there's this cascade, and we know that there's this famous power law of k to the minus 5/3, which means the velocity scales with the size to the 1/3 power. Many of you will know that. So the observations say, however, that this is steeper And we still don't really know why that is, but probably because the turbulence is supersonic, highly compressible instead of incompressible. So this water is incompressible, and therefore it has a different relation between the velocity and size, whereas clouds usually have this Larsen relation, as we have now come to call it, where velocity is size to the 1/2 power. So that means that we have a situation in the interstellar medium, probably, where we have, first of all, on large scales, at least in molecular clouds I'm talking now, not in the very much bigger ISM, we have probably supersonic motions here, and then ultimately, because the cascade reduces the kinetic energy, we have to have some transition scale, the sonic scale at which the turbulence becomes subsonic. So molecular clouds, about 100 parsec then maybe, and these filaments and cores, they form usually at a fraction of a parsec, where we think there's the sonic scale. So the sonic scale probably plays a key role in setting the size of the structures that then ultimately form stars, so the progenitors of stars, the cores and filaments. And then we have our planets and accretion disks on much smaller scales. Now, there could also be another cascade to the H1 gas. So we've heard in the previous talk about H1 and its importance. So because that gas is actually more transonic again, so there might be another sonic scale, which is just an idea that I want to inject here briefly. So we wanted to resolve this sonic scale on, at least in the molecular cloud regime. And for that one needs a lot of resolution, because we need to, or we want to have both the supersonic cascade and the subsonic cascade in this simulation. So we made a simulation that has 10,000 cubed grid cells, and we also have currently an MHD version of this in the workings. This is a pure hydro simulation, but we can at least use this in order to see these structures that make up these sonic structures that form at the sonic scale. So analyzing this, we have the turbulent velocity, or normalized by the sound speed. We have the turbulent Mach number as a function of scale. So you see now this simulation has a large dynamic range. So the scales here that are relevant are probably 3 orders of magnitude. Of course, the resolution is actually at 10 to the 4. But because we have numerical dissipation, we're not going to look at this much, because we know that 10 grid cells is not enough to say much. So this should be excluded, but we have the driving scales here and then some intermediate scales. And we can immediately read off the sonic scale here, because this is turbulent Mach number as a function of scale. So where this is 1, we have the sonic scale. And we can plot this a bit clearer by dividing by what we think is the scaling in the supersonic regime, namely size to the 1/2 power. And then that should be flat. So this bit is the supersonic scaling range, and this would be the subsonic scaling range. And these are the measurements of the different power laws. So we have about L to the 1/2, which we think is the appropriate value for supersonic compressible turbulence. And then we have about L to the 1/3. With intermittency corrections, you have a somewhat steeper exponent, L to the 0.39. And the sonic scale is not a sharp transition, but it's sort of a transition that's rather smooth, but it's a clear transition there. So it does exist, the sonic scale, and it makes a difference to have both the supersonic and the subsonic scaling range in a simulation. So why is this sonic scale so interesting? Well, we think that it marks the transition to where we form filaments maybe and dense cores, and we can actually derive a star formation rate in these theoretical models by equating this sonic scale with the gene scale, which is of course the size for gravity. And that gives us a critical density for star formation. So this is really a key ingredient for these theoretical models of star formation. So coming back to the question of what drives the turbulence, and of course we have people here in the room who have actually done pioneering work on these ideas of how turbulence is important in the process of star formation. So turbulence could be driven by a lot of different things, probably by jets, outflows, as I showed you in the beginning, but also supernova explosions, even gravity, accretion onto the galaxy, ionization, winds from stars, spiral arm compression, cloud-cloud collisions. All of these processes might drive turbulence in one way or another. There's basically this feedback path of driving turbulence, which is from stars that exist, that blow up or do jets or whatever. And then there's these things like cloud-cloud collisions, so the larger scale dynamics of the galaxy and accretion onto the galaxy. All of these processes will inject energy or drive motions of all sorts of different types with all sorts of different statistics. And so, for example, we can very, as a theorist, naively distinguish these processes in terms of its acceleration field. So we can say, okay, there's some acceleration field that drives turbulence, and maybe this is a more solenoidal acceleration field or a more compressible or compressive acceleration field, then the curl is zero here, the divergence would be zero. Put this in computer, run, and then you see the driving creates these very different structures. So it really matters how you drive the turbulence. Turbulence is not the same. It can also be supersonic or subsonic, as I showed you before. So it's not just turbulence. Turbulence has parameters, including how you drive it in matters. So make much denser structures when we drive compressively, which you can quantify with this density PDF, which many of you know. So there's a different relation between how wide the density distribution is as a function of sonic Mach number. Of course, if you drive the turbulence faster with higher Mach number, you also get a wider PDF. But also if you change the way you drive the turbulence, that totally matters for what kind of density distribution you get. And I know some of you will have seen that, so I'm not making this a big deal right now. But so if you do this solenoidal driving, the typical parameters for interstellar gas, so this is an 8 parsec box, in this case, no magnetic field for now. But solenoidal driving Mach 10, which we think is a typical sonic Mach number for these clouds in the Milky Way and elsewhere, this takes a lot longer to form stars than when we do compressive driving. So I can play this quickly again to show you how dense a structure you get when the turbulence is fully developed, which is now. So you get these very dense filaments that form stars really, really quickly, and this takes much longer. So it takes 20 times longer actually to form stars here. And theoretical model we've developed based on these pioneering works shows very good agreement between what we get from simulation and theory. Now, this is a newer thing where we also look at how does this driving mode of turbulence affect the initial mass function of stars. So we find that there is not a huge effect, but a measurable and significant effect. If you have compressive driving versus solenoidal driving of turbulence and otherwise everything the same, you get a peak of the IMF that is shifted by a little bit. So here you have a median of 0.6 solar masses, here of 0.4 solar masses. So there is a difference in the IMF when you drive turbulence differently. So clearly turbulence plays a role for the initial mass function of stars. So now question is, where is this driving different in different environments? And we can look maybe in the disk of the galaxy, there's cloud-cloud collisions, maybe supernova explosions, but in the galactic center, there's maybe a lot of shear, so the driving could be more solenoidal. We don't know that, so we're still trying to figure that out. But this is what we know so far. So when we make a plot of density fluctuations as a function of velocity fluctuations, then we have basically this relation between the two. And theoretically, I've shown you, and also with many simulations, that when we go in different paths in this diagram, then essentially the more compressive driving is to the top left, and to the bottom right we have more solenoidal driving. And here are these lines that say compressive driving and solenoidal driving in yellow. And so what we know is that, for instance, this galactic center cloud brick sits here. So it's more, well, it's supersonic slightly, Mach 5 or so, but it doesn't have as many density fluctuations. So measuring these things carefully is, of course, difficult, right? You need to really pay attention to how you derive the Mach number from observations, how you derive the density fluctuations. So there's various tricks that I can talk about more later. Thank you. But essentially, if we do that carefully, we can get data points in this space. And here we see in the galactic center, it seems like the turbulence is driven more solenoidally. So maybe there is more shearing motions induced by the very strong motions near the galactic center. Whereas these clouds up here, also in Taurus and other regions, but in Carina in particular, in this publication, these are probably dominated by ionizing compressive motions. Moreover, we went on to looking at the W and M, so the warm neutral medium, and now also looking at colder neutral medium. And in these laser experiments at the National Ignition Facility, we are measuring data points as well on this graph. So very, very different scale, totally different, you think, physical process, but in the end it's turbulence, so it's scale-free. So you can do these comparisons on such a graph. And also more recently in this publication, we have a map now of this turbulent driving parameter for the Small Magellanic Cloud. So we can have a look at where is the warm neutral medium in this galaxy. So this is with the ASCAP, the Australian Square Kilometer Pathfinder Array, really like state-of-the-art data now with H1 to look at how is the driving in these different environments. And without really knowing what's happening here, some regions are more solenoidal, some regions are more compressively dominated. This we need to figure out, but there's clearly a whole range of these driving modes present in a galaxy in different environments. So now coming back to magnetic fields in the last 3 minutes, maybe. So we can do these same experiments I showed you earlier, but now with magnetic field. So this doesn't have a magnetic field, and this has a typical magnetic field. So you get a sense of what the magnetic field does to star formation. So this is similar to before. Form stars at a reasonable pace, relatively fast actually. And this slows down the star formation. So magnetic fields slow down star formation. Magnetic pressure slows down the collapse. Ultimately, we would also have these jets formed by the magnetic field, not resolved in this type of simulation. But we have a slowdown by about a factor of 2 or so, as I showed you earlier, when we have magnetic fields. Interestingly, here also something you can see is the amount of fragmentation you get. So here you have 109 such objects, dense objects that are bound. Here you only have 63 such objects. So there is also a very critical effect of magnetic fields on the initial mass function again. So conclusion, you need all of these physical processes to understand star formation, unfortunately. We can also look at how the magnetic field looks like in this simulation when we draw the magnetic field with vectors here. So I want to show you the mess that this produces and the different environments, again, in which the magnetic field can be amplified and strong. So you get these dense regions that have very strong magnetic fields and very intermittent magnetic fields, very structured fields in places, very unstructured fields in other places. So it's a total mess and difficult to understand. So this is, of course, things that we also have pioneers in the room about how we can amplify magnetic fields via, for instance, the turbulent dynamo. And I'm out of time, but we talked about ISM multiphase media. So recently we looked at how is the magnetic field amplified exponentially and then saturates in these different cases of cold-warm media. So in the cold medium, the saturation level is a bit smaller than in the warm medium, but otherwise the growth rate is very similar. I'll just skip that real quick. So another thing about the dynamo is it's universal. So it doesn't matter really where you start from. It will amplify exponentially fast with the same growth rate and then ultimately saturate at the same level. Truth is also this is also true, for when you start with a very, very strong field. It will just decay down to the same level again, which we've recently shown. Finally, in these National Ignition Facility laser experiments, we're doing simulations for this. So we add tracer particles to trace the magnetic field in a Lagrangian frame of reference. So we can actually study how the field gets amplified while the shock is running over this structured medium when the laser hits this plate. And we also get a dynamo consistent with some of the models that we think are relevant for this. Finally, we have particle and cell simulations of the dynamo now. So these are collisionless dynamo simulations. So this is a new work where we find a critical magnetic Reynolds number for the first time in this. So very similar to MHD, but now for collisionless plasmas. And this is the very last bit, which is maybe interesting and triggering some discussion, but we'll see. So the question is always, what resolution do I need to get to a certain Reynolds number? Oftentimes in the community when we do like numerical simulations. So basically, this is a summary plot of a paper we put on arXiv recently that shows various data points from the literature of various different people, also people here in the room, and how their Reynolds number might be set compared to what the resolution of the simulation was. And with that, I think I'll stop.
Thank you very much, Christoph.
Thank you.
Time for questions. CRU, the first one, please.
Thank you. So I want to ask the transition scale between the two different slopes. Does it only depend on the Mach number? Does it also depend on the driving?
Okay, we don't know that.
Okay.
So we have not tried that out, but for now we only have this with mixed driving. So it's an interesting question. Okay. One should try this out with different driving modes.
So if you have a purely compressible driving, do you also see the solenoidal motions can develop spontaneously at smaller scales?
Yes, absolutely.
Okay.
So this is work that has been like during my PhD back in 2010. Right. So in the paper in 2010, there's a quantification of how many solenoidal modes and compressible modes in the velocity field you get when you drive with these extreme modes. You get lots of solenoidal modes also, about half-half.
So that transition scale could be also, I mean, comparing it with the sonic scale would be interesting, I think. Yeah.
Yep.
Thanks.
Mordecai.
Hi, Christoph.
Hi, Mordecai.
Nice talk. So I wanted to poke a little. You have a paradigm where you've basically got turbulent inhibited star formation. And I would like to compare that to turbulence produced by gravity and accretion during star formation, which I think we see evidence of in the higher diagram. So comparing the surface density, that is strength of gravity, to the variable parameter, that is how strong the turbulence is. In the turbulent inhibited model, where you're citing the Larson's law, which is sort of 1 point on the higher diagram, how would the whole higher diagram appear? Because that seems to be gravitationally dominated.
So you're asking about this diagram. So yeah, that's the thing. We don't really know what gives rise to this relation. So it could be gravity. I think that's what you're trying to get at.
Absolutely.
That's true. So in a virialized situation, you can also derive this relation just by saying E graph equals
the square root of 2 different.
Yeah. Yes, that is a possibility. I mean, we do get it from turbulence alone, though. So in principle,
we get
both
this
is
relation,
possible.
But if you go to different column densities, you get a different relation, which turbulence alone, I don't think should give you. Let's talk more about it.
Yeah, sounds good.
Any other questions in the meantime? I have a question regarding the... Oh, you have a question,
no,
yes.
Go ahead.
I have a,
please.
No, please go ahead. I'll ask it afterwards.
Oh, I have a short question related to the dynamo, because you went too fast through those.
Yeah, sorry about that.
About the Reynolds number that you get in the collisionless, this 300 or 400, something like that. And I think it was in the collisionless test, right? So meaning that it might fit the intergalactic median dynamo, right? But what, I mean, if you translate this to physical scales, does it really match intergalactic medium conditions or intercluster medium conditions?
Yeah, intra-cluster medium or intergalactic medium conditions, I think it would. Of course, these are dimensionless simulations,
of course.
But I think it would.
Right.
I mean, this is, of course, the main application that we have in mind for this.
Right.
So we do this with Mach numbers around 0.2, which we think is appropriate for the intra-cluster medium. And basically, otherwise, also with physical conditions that would be appropriate for that ICM.
Right. Yeah, we can talk.
Thank you very much. Yuan, next question, please.
Hi.
Hi, really nice talk. So I have a question sort of related to what Mordecai mentioned. So if you have turbulence mostly driven by gravity, would you mostly get compressive modes? And if you look at the B parameter, what do you get? And also when you, sorry, it's like two questions. And when you look at these different clouds like Taurus and small magnetic cloud, in that diagram you showed us, I think you were mostly showing just one phase, right? So if you were to look at, it's much later, it's when you, So when you look at the different phases within one cloud, what trends do you see?
Yes, so it's very much a question of the phase, indeed. So the warm neutral medium, of course, it has Mach numbers of around unity. So sorry, I went through a lot of this stuff too quick, so it's good that we have questions. So this is a medium that we think is about transonic, which is also the thing I pointed out about the extrasonic scale. So ultimately, you can have this warm neutral medium. It's turbulent, of course, so you have compressions there also. But mildly so. Nevertheless, there's material coming together from time to time to form these cold neutral medium and ultimately molecular medium phase, where the gas cools very quickly and then becomes supersonic. And then this is the phase that we're in here, so in the supersonic regime, where we have molecular clouds. And there, it's also a mix. So you can have in the central molecular zone, you might have more solenoidal driving. In clouds in the galactic disk, you can have more compressive driving. So it really depends on the environment and the drive of the turbulence. And you asked about gravity as a driver. I think we don't really know that, what it does. So that's why I'm at least still encouraged to try and figure that out with simulations that are dedicated to doing so.
Thank you. Next question.
Fascinating videos you have there.
Thank you.
I have a question. When you're creating those simulations, so you've got where are the I don't see, I see a lot of this literature, but I don't see where are the formulas that are driving the simulations, and where is the delta T? And so can you tell me what papers really get into the nitty-gritty of these simulations are fascinating, but what are the inner workings of them?
So that's a good question. Of course, I left all of the details out of the talk because those are really details. But the equations that we solve and the numerical methods that we're using are described in detail in the publications that I cited.
Who's kind of the number one person? I mean, which citation?
For what?
For the simulations.
Well, I'm doing the simulations, and I developed a lot of the tools. For instance, the star formation model and the jet module I developed, also the turbulence driving module I developed.
You can.
Yeah, of course, based on a lot of work that has been done by many, many others before me.
So I'll ask Alexei to connect his computer. If there is another brief question in the meantime, no. If that's not the case, then let's thank Christoph again. Thank you.